So remember Legendre's theorem says that a polynomial of degree, you have to be in a prime modulus. A polynomial of degree n has at most n different roots, right? And so 2 and negative 2 are certainly roots, but we have to be concerned that there could be others. Okay, so but anyway, 2 is going to be a primitive root. So note that r equals 2 is a primitive root. Okay. What that just means is that it has order 12. And in fact, if you want, you can take all of the powers of 2 and reduce them in mod 13. I'm just going to do this for the sake of reviewing. We don't really need this for the problem, but I'll do it anyway. If you write out all of these powers, not very many, there you see that 2 to the 6th is negative 1. We just keep going here. 2 to the 7th. Maybe I should be using some positive numbers too. 2 to the 9th would be 18 is 5. 20 is the same as 7. And then you get back to 1 again. Okay, so there's your list of all the powers of 2. Using that, of course, you can build your index table if you want to. Don't really need to, but why not write it down just to review it real quick, how that table is made. We're going to spend a long time on this particular problem. It's covering a lot of stuff, right? We're still on the first equation, trying to reduce it. So we've made these tables before. We're going to make the index table for x relative to the primitive root 2. So we just write down all of our numbers up through 12. 9, 10, 11, and 12. And then we just start calculating, well, we just use the information that we have here. So the index of, well, 1 is either, you can think of it as either 12 or 0. 2 was the first power, so 2 to the first gave me 2. The index of 4 will be 2, the index of 8 will be 3. See how this works? So this is like the power of 2 that gets you the number that's above it. Okay, so 8 is above 3, so 3 will be giving me 4, 6 gives me 5, negative 1, which was the same as 12, gives me 6. And then 11 gives me 7, 9 gives me 8, 10 and 10. Oops, I skipped. 5 gives me 9, 10 gives me 10, and 11. So there's your table of indices right there. Everybody okay with that? Definitely want to be able to draw out that table. So really, yeah, so that's basically it. And of course, when you're working with the index equations, it's always mod phi of n. So in this case, these are all going to be calculated mod 12. So for example, you can take this 12 right here and change it to a 0 if you want to. It's the same thing. 2 to the 0 is 1. 2 to the 12th is 1. It's a mod 12 calculation for the exponents. Okay, so having done that, I can take the index of both sides of this. So the index relative to the primitive root 2 of x to the 6th is congruent to the index relative to the root 2 of negative 1, and this would be in mod 12. And of course, negative 1 here, okay, that's not the first thing I noticed, it's not on my list there, but negative 1 is, of course, the same as positive 12 in mod 13. So I can think of this as the index of 12, which is 6, right? So this is 6. And then remember, yeah.
Even though we're in mod 12, we don't think that -1 is 11?
No, we're in mod 13.
Over there, but now we're in...
But we're,
Oh, okay.
but the thing that's being inputted into the function is a mod 13 number. Then I take the index of it, and the value that I get will be viewed in mod 12. Right? Everybody with me? Okay, good. And on the left side, we have our properties that are just like logarithm properties, which means I can pull the 6 down in front, and the index of x with respect to the primitive root of 2 is what I have there. Okay, so this is the equation I come up with. Okay, does that equation have a solution? Well, it's a linear congruence. Basically, there's a common factor of 6 throughout the entire congruence, so you can essentially divide that out. Okay, this is just another way of saying that 12 divides the difference of these two numbers. So if you took a factor of 6 out of both the 12 and the difference of these two numbers, you would just end up with the following congruence. Index of x is 1 in mod 2. And that's really just another way of saying that the index of x should be an odd number. So you're just looking for the odd numbers in the list, and those are the x's that will solve this congruence. Okay, so coming back, I guess I can get rid of a lot of this stuff now. So coming back to the original problem, essentially I just have to take the odd, the ones that are odd in this table, okay, which is half of them, and the x's that are above them are the x's that will solve the congruence. There's 6 of them, right? It's exactly the number of roots that we were allowed to have. Okay, so x is congruent to either 2, or 5, or 6, or 7, or 8, or 11 in mod 13. Okay. So there are a lot of options here. A lot of options so far. Okay, so far so good. That's the simplification of the first congruence. So in theory, we're going to have to pair that, we're going to have to pair each of those choices with the second one. It's going to create a lot of options for the solutions here. I may not do them all. Okay. These should be, of course, notice that it's very symmetrical. The 2 and the 11 are just negatives of each other. And so is the 5 and the 8, and so is the 6 and the 7, which totally makes sense, because if you find one x that works, its negative will also work. So that's what you've got. You've just got negatives paired up like that. Okay. So far so good? Let's look at the second congruence real quick. Second congruence says 16x congruent to 26 mod 50. Does anybody have a suggestion of how I can start trying to solve that for x if it's even possible?
Take out a factor of 2.
Okay, we can take out a factor of 2. So let's look at 16x congruent to 26 mod 50. Take out a factor of 2, and we get 8x congruent to 13 mod 25. Okay, that's certainly true. And from there, what can I do? Or what should I do?
Find the inverse of 8.
Yeah, I can clearly see, I'm really trying to get rid of this 8 to solve it for x. So the question is, does 8 have an inverse in mod 25? The answer is it sure does. You can probably do it in your head. Because 8 times 3 is 24. I don't really want 24, I want 1. I want 8 times something to equal 1. But what could I, instead of 3, what could I multiply by? Negative 3. Because negative 3 is going to give me negative 24, which is the same as positive 1. So I'm just going to multiply through by negative 3, and that will give me x congruent to negative 39 Negative 39 could be changed in mod 50, or mod 25 could be changed to 11, just if you want to use a positive value, and that would be mod 25. Okay, so far so good? So we, for example, so we have a number of simplified versions of the original two congruences. One of them is x congruent, I'm going to just take the first one up here. X is congruent to 2 mod 13, and x is congruent to 11 mod 25. Now you're in the ideal form of a system to be able to apply the Chinese remainder theorem to it. Okay? Does everybody know how to do the, I can't envision a final for number theory not having the Chinese remainder theorem on it, so you want to make sure you can use it and apply it. So everybody, probably because you had to work on it for your recent papers, you might have it pretty well in mind how it works. You basically call these two numbers A1 and A2. This is just a system with just two equations, so it's actually pretty easy. And then you have an N1 and N2. Remember what those were? For this system, what would N1 be? 25, and N2? 13, good, okay. And then Y1 is supposed to be the multiplicative inverse for capital N1 in mod little n1, which is 13. So, so in other words, we have to have 25 y1 congruent to 1 mod 13. So can somebody tell me what y1 could equal? Yeah, 25 is the same as negative 1, right? So if 25 is the same as negative 1, then if I multiply it by negative 1, I get 1. So that's perfectly good. You don't have to count. There are many other choices for y1 that are also fine, but you only need one. Because ultimately the CRT is going to give you a unique solution modulo the product of these two mods. Okay, and then for the second congruence we have 13y2 congruent to 1 in mod 25. So this is, hopefully we can eyeball that one. What would I choose for y2? 2, right? 13 times 2 is the same as 1 in mod 25. Okay, so then once you have that, you just need to be able to write down the answer, which I think you probably remember because it comes up a lot, right? So the solution is x congruent to, you know, a1, n1, y1 plus a2, n2, y2, and this will be modulo the product of those mods, which is 13 and 25. 13 times 25 is
325.
325? Yes, 325 sounds right to me. Mod 325, good. So this is negative 50 plus, let's see, 26 times 11 to 86. Okay, and that comes out to 236. Mod 325. So 236 could be, if you prefer, you could reduce it to negative 89. It's the same thing. It's a little bit smaller value. So that is one solution. That is one solution to this pair of congruences back here. Okay. So any x that is of that form. Okay. But you got all these other choices too. You can, yes. Mod 325. Thank you. You have many other values of x to consider as well. So I'm just going to say by similar reasoning, you can find other x values. And unfortunately, I don't have them all worked out, so I'll just have to let you guys play with that a little bit on your own. Okay, that makes sense? So use indices really to simplify the first one, and we divided out any common factors that we could to simplify the second one. Yeah, Fran?
So if we get the 6 different answers,
Mhm.
we're just gonna have 6.
You have to write them all down.
Okay.
Yeah, it's just a big long list of solutions. Yeah, Jewel?
I had a question,
Sure.
since this is negative 89 in mod 325,
Uh-huh.
but originally we had mod 50 and mod 13.
You would still want to just present your answer in mod 325, right? Because this tells me very clearly which, I could actually list out what are the values of x that satisfy this congruence and that are equivalent to negative 89 in mod 325. So you definitely want, it's a very good point. You don't want to, this looks like you would be giving a solution in mod 650. But you're better off giving, and we've seen this happen before, whenever you, it's basically because we divided the second congruence through by 2. Once the second congruence was divided through by 2, this congruence had a unique solution for x. But that unique solution was a unique solution modulo 25, right? Namely, x was congruent to 11 mod 25. If I wanted, I could go back and say, no, I want to do everything mod 650, right? But in order to do that, I would have had to say, I would have had to give you 2 options here, right? I'd have to say, oh, well, in mod 50, x is either this or this. So now, right, you're giving me double as many options, but you're making the mod bigger. But why do that, right? It's just easier to just shrink the mod down. Does that make sense to everybody? Yeah, okay. A lot of times what I like to do with these kind of problems is say, give me the smallest solution or something like that, so you're really getting a unique answer. So the smallest positive solution, for example, would be 236, at least for this first case. Okay, that's not to say there wouldn't be others that could work as well. Okay, so that gives you a little bit of an idea. Okay, let's see what other cool stuff I came up with here. I kind of want to mix things up and move around, so I'll choose something different for a little while.
Just a quick question. This is 2, and you said 11 is congruent to -2. If this were to show up on an exam, could we just say, oh, instead of -50, then we know it has to be +50, like in the solution to the Penning remainder theorem, since we know it's just going to be negative, the opposite of 2.
So just doing it with -2 instead, in the Chinese.
Oh, you mean you want to use -2 here?
Right.
Yeah, so
Oh.
instead of having to show all the work again, we just
Yeah.
get a +50 for our a sub 1, n sub 1, y sub 1, correct?
Yeah.
I have one thing to say about that though. When you're using the x congruent to 11 case, it's easier than that since you're trying to solve x congruent to 11 mod 13 and x congruent to 11 mod 25. So you don't really need
But for the other
one.
ones, like
Yeah,
for
I'm
5,
talking
you
about
do it for
example.
5
So
and
if
6.
I change
but
this to the -2
Yeah.
case, you're saying,
A1
I mean,
changes.
it would just save us
just changes
time.
this to -2, you mean?
Yeah, and so then it would be a +50 instead of a -50.
Yeah. Yeah, that's fine.
So we
So
can-
nothing else changes.
So we could just say that in terms of like if this
Sure.
popped up on something.
Yeah, nothing else is going to change except for that number right there, right? Yeah, because that's a good point. The second equation isn't changing, so and neither is any of the mods. For all 6 of these cases, right? The big N's stay the same, right? So therefore, and the little n's stay the same. Therefore, the y's are the same, right? The only number that's changing is really this one. So that's what Jeff is saying. I don't need to like write it all out every time. You just come replace this one number with some other number. Yeah, that's certainly true. Okay. Good? Everybody good on that? All right, let's move on. Practice some other stuff. I'm going to, as I said, mix up the order of things here a little bit just to keep things going. Let's do this one next. Let's prove that a number of the form 3 to the I times 5 to the j can never be perfect. Okay, try this one. Well, at least I hope it's not. Actually, if this weren't true, then we'd have an odd perfect number. So, if there are no odd perfect numbers, then this one's not gonna ever be perfect. So, how would you suggest we approach a proof like that? By contradiction, why not? Okay, so assume by way of contradiction that n, which is equal to 3 to the I times 5 to the j, is perfect. And what's the definition of perfect again? What is this doing? Sigma, right, sigma of 3 to the I, 5 to the j would be equal to 2 times 3 to the I times 5 to the j. Right. Okay, so that would be the equation that hopefully is going to give us a contradiction. Do we have any way of, well, maybe I don't want to jump in too fast. So do you guys have a suggestion what we would do next?
Yeah, complete sigma.
Yeah, we ought to be able to get an expression for the left side. Okay, so let's see if we can work on the left side for a second. Sigma of 3 to the I, 5 to the j. Bells should be kind of going off here. This is like a couple of things multiplied together, so what can we do with sigma? Split it apart. Remember guys, if the numbers that you are working with are relatively prime, sigma is multiplicative with respect to their product. So is tau, and so is the Euler phi function, right? They all respect multiplication. So it's like a universally true thing, as long as these are pairwise relatively prime. Or as long as these are relatively prime. So this is just sigma of 3 to the I times sigma of 5 to the j. Okay. Sigma is the sum of all of the divisors of the number. Okay. So what am I going to do to write down what sigma of 3 to the I is? Go ahead.
Use the geometric series.
Good. So the divisors of 3 to the I are just going to be smaller powers of 3, leading up to 3 to the I. So this is just going to be, and it's a series because we're going to add them up, right? So 1 plus 3 squared, up to 3 to the I. Okay, and I'll do the same thing with the other one. So I'll have 1 plus 5 squared plus plus 5 to the j. That's what sigma of 3 to the I times 5 to the j is. And we assumed in the beginning that this comes out to 2 times 3 to the I times 5 to the j. All right. Any ideas what we can do now? We're trying to get a contradiction out of this equation.
Well, we know that last term
Mm-hmm.
would be 3i, 5j.
Now the biggest term on the left side is actually half of the right hand side. So the right hand side is 2 factors of 3 to the I, 5 to the j. So if we were to FOIL this out, then we would cancel that thing, right, from both sides. That'd be one thing we could do. And then we'd have a lot of other terms on the left side that would equal 3 to the I, 5 to the j.
And just use the formula for the series.
Well, so we also have a formula. Okay, that's another idea. We have a formula for the finite geometric series. Let's just see, what would that give us? So this would be, what is the formula for this?
3 to the I plus 1
3 to the I plus 1
minus 1
minus 1
all over 2.
all over 3 minus 1, which is 2. All right, good. Times, and then how about the other one? Okay, minus 1, good. Or 4, perfect. Okay, so we get that, and so that's still equal to 2 times 3 to the I times 5 to the j. So this is good. Stephen, I think the thing with your suggestion, you noticed something that is very, very good, which is that this top term can cancel with this one. The trouble is if you actually do kind of FOIL the whole thing out, you're kind of left on the left side with just a soup of different terms that and they're all smaller than what's left on the right side, so it's not obvious for sure that there's a contradiction there.
Yeah,
But it was like the first thing I saw as well.
Yeah, because I wanted to pull that over,
Mhm.
and essentially.
But then you're gonna have to figure out how to write down all of the other terms in
Yeah,
this.
no, I know, that's why I said that's why it's not gonna be.
But- Right, no, it's a very good initial thought, absolutely. Yeah, Lisa?
Can we multiply both sides of that equation by 2 cubed?
At this one?
Yeah, because then the
Oh, to get rid of the
To
fraction.
get rid of the fraction.
Oh, yeah, let's do that. That's what I was gonna do next.
Oh, okay.
Yeah, let's get rid of the denominators. So, right, we don't like denominators in this class, we're doing whole numbers. So, 3 to the I plus 1 minus 1 times 5 to the j plus 1 minus 1 is equal to, that'll turn into 16, 3 to the I, 5 to the j. Okay.
Can we then make an argument of inequality?
Yeah, I'm open to that. Oh, like how? That would be,
Scratch that. Maybe like an argument with division. We know from previous exercises that any power of an odd number is always odd. That any odd number minus 1 is always even.
yeah, so this is even,
And same
and
thing.
so is
with
that,
the
they're both even.
But that equation implies that 3 divides those two terms. Or if not 1, 3 has to divide one of those two terms since it equals both sides,
Yeah, yeah, there's factors of 3 over here.
which are odd.
By the way, I should stop for just a second. If either I or j was 0, if either I or j was 0, so you just had a power or a prime, then we go back to your homework assignment that you just got back. One of your problems that you just did for the last assignment was you proved that no prime power can be perfect. So p to the k can't be perfect. So if either one of these, so maybe we should just say I and j at least 1, because if either of them are 0, then you can revert back to something simpler. So, right, so there's at least one factor of 3 here, and at least one factor of 5 here, so on the other side of the equation, there must be also, by the uniqueness of the fundamental theorem of arithmetic, there must be at least one factor of 3 on the left side, and one factor of 5 on the left side. And of course, this part doesn't have a factor of 3 in it. Right? Because if this was divisible by 3, then if you subtract it from just this, which is also divisible by 3, you'd have 2 consecutive numbers that were divisible by 3. That doesn't make sense. So basically, what you've proved is that 3 has to divide this one. And by the same reasoning, 5 has to divide this one. Yeah, Warren?
Well, 3 to the I has to divide that, right?
Yeah,
All of
good
them.
point. Yeah, all the powers of 3 that are here, they're all going to have to be inside of here. Exactly right. Okay. So, good reasoning with this with this fundamental theorem of arithmetic on both sides of the equation. I still don't quite see how to make this work. The trick here is actually to take the 3 to the I plus 1 and write it as 3 times 3 to the I, and take 5 to the j plus 1 and write it as 5 times 5 to the j. So let me do that. So this is 3 times 3 to the I minus 1 times 5 times 5 to the j minus 1, okay, equals 16 times 3 to the I times 5 to the j. So we just leave the right-hand side the same as how it was before. And if you actually have the potential to FOIL this now, right? It's not that bad. At 2 terms here, 2 terms here, then you actually just FOIL the thing out, right? If I FOIL this out, what am I going to get? I'm going to take this one times this one.
15, 3 to the I.
15 factors of 3 to the I, 5 to the j. That's this times this, right? And then what else am I going to have? Minus 3 times 3 to the j, minus 5 times,
3 to the I.
sorry, 3 to the I. I knew you said something wrong there. 3 times 3 to the I minus 5 times 5 to the j.